We're moving into a little smaller scale in the weather this week. We're going to talk about thunderstorms and tornadoes. Uh, First, we went through all the different variables that make up the weather, and then we began looking at circulations at a planetary level. Came down to our area, the mid latitude. Now we're going to come down to thunderstorms. Thunderstorms develop when the air is pretty unstable. So let's look at some of these things. Uh, there was a super tornado outbreak in 2011. It's actually the most active season in the history of tornadoes. Uh, in that year, just during the springtime, we had 1,243 tornadoes in the United States, way more than anywhere else in the world. Pakistan actually is the next most, and they get about 30 to 40 in a year. So the United States dominates in tornadoes. And interestingly, we're going to look at why that happens. But during this tornado outbreak, there was one day, an outbreak of 25 to 28 April, when there was 342 tornadoes in 21 states, and 321 people died and over 10 billion in damages. So you can see tremendous amount of tornadoes may occur at any time in our history. And this was actually a look at tornadoes that developed on the 27th of April. There was a very significant amount of warm, humid air out ahead of the cold front, great wind shear, the humidity and the heat helped increase the instability. Uh, and they went all the way in. Some of these convection went all the way into the lower stratosphere. Of the 200 tornadoes that touched down, there were actually 4 EF5s. One of those EF5s completely swept away a brand new brick house, including its foundations. We even removed sections of asphalt and picked up an anchored 800-pound safe. So you can see the power of the winds in these EF5 tornadoes. And you can see some tracks here, here. Amazing the damage they did. And this is an EF4 tornado, what it looked like in Alabama on that day. And you can see rotation around the cloud. And interestingly, in later pictures, you would actually see people driving on this road towards where that tornado was. Still confuses me why they would do that. And here you can see some of the damages from a different outbreak. And when I've done surveys of tornadoes and all, we can see, all the floors are lifted out. I want you to notice here that in this house, where these 2x4 was going across, there were bolts anchored from the concrete out. They literally have big, strong nuts on them. This is what actually holds the house into the foundation that's there, into the ground. We have done surveys, and others have done surveys of tornado damage where these bolts were never connected. When that happens, it's very easy for a house to have a lot of extreme damage. So now that we've talked about a little bit about tornadoes, let's start with the thunderstorm, the basis here. Thunderstorms are mesoscale systems. They're accompanied by lightning and thunder. That's the definition of a thunderstorm. So what happens is when you look outside, you'll see a towering cumulus cloud. All that towering cumulus cloud is all air going up. We talked about air parcels. That is an air parcel that's rising. At some point, precipitation begins to develop in the upper part of the cloud. The precipitation gets heavy enough to begin to push the air back down, and you wind up with a rain shaft. So this would be the front of the thunderstorm as it's approaching you, and this would be the back where the precipitation was. So you can see actually the warm air lifting up, dropping down where the cooling is occurring in the thunder rain shaft. And when it comes to the end, what you wind up with is hardly any air going up. All the precipitation is just falling out. That's the 3 stages of a thunderstorm. Towering cumulus stage, mature stage, that's when the worst weather is going to be, and the dissipating stage. So cumulus clouds can surge up literally 26 to 33,000 feet in 10 to 15 minutes. They can be triggered by a lot of different things. Usually free convection, like occurs in the summertime when it's very intense heating, are not going to produce necessarily severe thunder. They may produce a lot of rain, but they may not produce the severe weather. Whereas forced convection, such as with the frontal pushing or orographic lift over mountains, can really generate the lift needed to cause these thunderstorms to become severe. This is just a picture. On this radar, you can actually see what literally is an outflow from a thunderstorm, this thunderstorm. And this is gust on thunderstorms that actually occurred way over here undeveloped and went out to that way. A lot of times where these outflows come together, new thunderstorms develop out ahead of them. And you can see 2 new cells are developing right here. And if you look at these, you see a roll cloud here. It's a cloud that literally looks like it's rolling along. It's separate from the thunderstorm. And because of that, and the roll, I mean, it can bring you some bad weather, but it's generally not considered severe thunderstorms. However, look at this cloud. They call it a shelf cloud because literally that's where all the warm air is shooting up here, forming a shelf out ahead of the deep precipitation behind it. These kind of things are at the leading edge of the gust fronts, like you're seeing here on the radar. And that's where the most severe weather is. So when you're looking at a thunderstorm coming towards you, if you look at one and you see a rolling type cloud, it may be nasty, but it's probably not going to be severe. But if you see this shelf cloud like this, those are the ones you want to be very careful and seek shelter when they're coming towards you. We classify thunderstorms as a single cell thunderstorm, multi-cell cluster or multi-cell line, very similar, just the shape a little different, and supercell. So in a multicellular storm, you have a series of thunderstorms literally feeding off each other. And what happens is you'll have one cell, usually on the southern end, that's developing. They get stronger as they begin moving into the system, reach its peak, then it weakens and dissipates. And notice that these storms are all moving towards the northeast, but because the new cells are always forming way down here in the southern end and continue to form down there, the actual translation of this storm's cluster of thunderstorms is to the east. So while the individual thunderstorms are moving northeast, the actual area of thunderstorms is moving to the east. Here is a squall line, which is the cluster of thunderstorms. Notice that up here, it has a little curvature. It looks like a hook echo almost. It's much bigger. What that is an area of low pressure that develops on the northern side of the line. This is an area where we'd look for tornadoes, possibly more of the severe wind. But you can see how the line is bowing outward. That's because the wind is pushing it out in this area most. Not as much down here. And here you can actually see what an MCS, a multi-convective system, looks like on the satellite. Large area, very high tops with an extreme in one central part. This area would cause a lot of heavy rain, potentially severe weather on the outskirts of it, but then you may go into an area which gets heavy rain for hours on end. So what conditions do we need? We want maritime tropical air. Why? Well, we know that the maritime air is warm and humid. And that's what you need because when it's lifted up, condensation occurs, more heat is released, and that air has become significantly warmer than the surrounding air, so it can continue to rise up. Lifting can be mountain slopes, which happens in the Rockies or the Appalachians, or it can be by convergence of surface winds, particularly along a front. And that front could be a cold front, a warm front, or a sea breeze front. So initially, solar heating is going to drive all this. Most thunderstorms occur in the warmest part of the day. Uh, we're going to look at some upper air soundings here that are going to show you a reason why that is. In the Mississippi Valley, however, there's a low-level jet at night that develops, and this contributes to a nocturnal maximum of thunderstorms sometimes, so that they can get significantly severe thunderstorms in the middle of the night out in that area. And here you can see where most thunderstorms occur. Notice the peak is down here in Florida, where the most maritime tropical air. You would say, oh, Hawaii should be the same, right? It's in the middle of the tropics. However, it's under the trade wind inversion. Remember, we talked about under the trade wind inversion in planetary circulations, the air got stable aloft. That is what happens in Hawaii. So a lot of showers can occur, heavy rain can occur, but they don't get high enough to cause thunder. And that is all because of that trade wind inversion. However, in Florida, there's no trade wind inversion, and we get lots of thunderstorms. Notice here on the Rocky Mountains, there's another batch maximum of thunderstorms that occurs here from the wind coming into that area, lifting storms up. Florida gets the most thunderstorms in the U.S. The reason is it's a nice peninsula and you have a sea breeze from the Gulf and from the Atlantic. When they merge or hit the middle of the state, they form thunderstorms. I got caught when I first went to Florida State, which is right here. I thought that, oh, these thunderstorms are to my east and I'm not going to have to worry about them. Well, in the summertime and early fall, many times the flow is from the east here towards the west. And what happened that day was these thunderstorms formed over the central part of Florida and just gradually lifted and moved towards the west, and I got soaked. All because I didn't realize that thunderstorms that time of year moved that way. I learned real quick. Uh, Severe thunderstorms. There are very specific definitions for severe. One of them is you got to have at least 58-mile-an-hour winds, and hailstones have to be greater than 1 inch. We do not consider heavy rainfall or a bunch of lightning to be severe. They may do damage, but the lightning actually is not a criteria. The reason you need vertical wind shear is that change in direction keeps these updrafts going upwards instead of to the side, and it does not allow that cold air that comes down behind the thunderstorm, produces an outflow. That outflow cannot go out ahead of the thunderstorm. When it does, it begins to kill the thunderstorm. New thunderstorms may develop on the outflow, but that outflow will eventually cut off all the warm, humid air coming into that storm. That's why with vertical wind shear, the outflow can't go very far ahead, and the thunderstorms tend to stay upright. So you keep this very strong updraft going. Instead of maybe 5 or 10 minutes of it, you're getting hours on end of that. That allows the thunderstorms to develop and become severe. All right. This week, one of the questions you may get asked is, what causes the severe weather outbreaks in the Midwest? Very simply, there's a very significant extratropical low developing, usually to the east side of the Rocky Mountains. Nice warm front, plenty of moisture coming in off the Gulf of Mexico. From the west, we're getting continental polar air, and even maybe out ahead of it, continental tropical air. So you wind up with a lot of dry air, colder, and you're a boundary in here, a lot of maritime tropical in this area. So you wind up with a significant temperature contrast and a significant moisture contrast. And because you're getting very strong southerly winds on the low levels, and in the upper atmosphere, you're getting very strong southwest winds. Look at the wind shear, almost perpendicular to each other here. So it's very significant wind shear. All of that comes together to create severe weather in the Midwest. When you get all these ideal conditions perfectly, you can get major tornado outbreaks. And they can develop further east as well. But this is a very typical area to get them. All right, we want to talk about that heating. In the morning, many times, you'll wind up with the temperature inversion, maybe at, 2, 3 kilometers up. So at that point, yeah, your atmosphere may be unstable and moist down here, but if I start a cumulus cloud, it's going to hit this and stop because the air is going to not be able to break through it. But as the daytime heating continues, and maybe I get temperatures in the 90s over here, all of a sudden I'm breaking through that temperature conversion and have all this pent up energy down here. So that air is going to want to fly upwards because the air is much colder significantly with height here. And it's just going to take off. And that is when you get severe weather because you've increased the vertical motion significantly. Modest clouds are another example of what forms underneath a thunderstorm. Modest clouds very simply form because there's cold air aloft. That cold air begins to sink. It's become stable. Now, as it's sinking, the ice crystals in it are evaporating, and that causes the clouds to keep forming, condensing. Lightning. There are different ways we detect lightning. Obviously, you can see it if you're around it, but from a meteorology sense, we want to be able to see it over a large area. We want to know how frequent the lightning strikes are. Believe it or not, when lightning strikes start increasing significantly, that's a tell that severe weather may develop, such as strong winds or even tornadoes. So we're looking for that as part of a warning situation. There are lightning detection networks around the United States, and satellite now has a lightning mapper, literally picking out every time there's a flash in the atmosphere. So how does lightning form? Uh, Grapple, it's kind of a wet snowflake or piece of ice. And they go upwards and downwards in these thunderstorms. Grapple is a little heavier than main ice crystals, so they're going to tend to descend. Small ice crystals will move up. Interestingly, temperature is less than 5 degrees Fahrenheit, very cold. Grapple is negatively charged, and ice crystals are positively charged. Well, we have a separation of charges there, so we're going to know that the negative charge and the positive charge will want to cancel each other out at some point. So ice crystals are going to go up to the top of the cloud where it's coldest anyways. They're going to stay positively charged. Now, as you go down towards the base, you're getting more and more change in temperature. And all of a sudden, we switch. We have a positive charge for grapple and a negative charge for ice crystals. Again, separating out where charges are changing, and it's going to allow, you might get lightning up here. Now you're down here, it's going to switch. So you wind up with steps where the lightning transfers down to the ground. Another thing that's very dangerous in thunderstorms and why aircraft do not fly anywhere near them if they can help it, because there's been too many wrecks in the past. You wind up looking and you have a very strong downdraft. We talked about the outflow. Planes need a fairly constant wind in order to make it into an airport and know what their control, how to control their lift on their plane so that they won't go up too high or down too far. And in the past, when we didn't have good networks of checking out downdrafts like this, there are now radars at many airports that just look for this signature where these are going to occur. And by getting that, they can warn the pilot, oh man, don't go into that runway because you might run into this. All that would happen, as you can see very quickly here, is if you come into the downdraft, pushing you, come all of a sudden headwinds, your plane's going to say, oh, wow, I can go up much easier now. So you're going to have to correct for that. And very quickly, you go actually the opposite way and get tailwind. Now you have no lift. And if you don't make the corrections quick enough, you're going to hit the ground way too early. Derechos are long straight line wind damage. If you have an MCS, typically they form from that. And you had one in West Virginia a couple of years ago where the thunderstorms developed just to the west of Chicago, moved east with time. As they came east, they developed a very strong outflow along that tracked right with them. And that outflow had numerous gusts over 58 miles per hour. There was large area warnings issued, and that literally translated all the way to the Atlantic Ocean, causing damage all the way. You can see here how they develop. A cluster of thunderstorms starts developing, growing, and then they literally get that little curvature here and have like a comma shape to them, and they'll just translate to the east very, very quickly. And here was the damage literally coming down through that area. All right, another aspect of severe weather with these thunderstorms is flooding. All right, these all form in maritime tropical air masses, and they can have a tremendous amount of moisture in them. So what happens is that strong updraft causes really significant condensation to occur. When that occurs, forms large raindrops. And once that wind starts coming back down, it really can pull tremendous amounts of rain out of that cloud down to the ground. That's where you're going to get tremendous rainfall from that. One of the biggest flash floods in history was, well, we just had one last year in Texas. We had another one in 1976 in Big Thompson Canyon, which is just a canyon that comes out of Estes Park and comes down, literally winding up all the way in Nebraska there, in Kansas, I think. Uh, and that flood produced a wall of water about 15 to 20 feet high. All the rain occurred up the canyon at the top of it, so that people that were camping in the bottom of that canyon never even knew it rained. And many of them, when they got the warning, decided they were going to drive out. And fortunately, the windy road, they couldn't make it out of there in time. All they had to do was climb up the rock wall next to them, 15 to 20 feet up, and they would have been perfectly safe. But most of them chose to drive, and in that case, a lot of them died. Hail, the last aspect of severe thunderstorms. It's usually greater than 0.2 inches. Hailstones form when there's a lot of water in there, and that water begins to get cooled, ice begins to develop, and the ice continues to move upwards vertically because of the strong updraft. When it does, it grabs all the water droplets around it and keeps growing bigger and bigger till you wind up with a big hunk of ice. And you can actually see, when you're looking at it with dual pole radar, you'll see these areas of ice crystals forming into hail up in the upper parts of the clouds. They'll gradually work their way down and eventually hit the ground. So they use dual pole all the time to detect these. Tornadoes are the last part. We talked about those earlier. They're generally small and short-lived. Some of the big ones, however, can last thousands of miles on the ground. And yes, even West Virginia gets tornadoes. Had a lot of students tell me they don't get tornadoes in West Virginia. You do. You actually average 2 or 3 in a year. And I was there one year when you actually had 15 in one year. So they can occur in West Virginia, and they can skip from mountain range to mountain range. Very strange system. Funnel clouds are usually the first indication. They're very low pressure, air rising and cooling because of the low pressure, literally get condensation and form a cloud down near the ground. It becomes a tornado when the ground touches the ground. Otherwise, it's just a cloud aloft. There are very, very strong pressure gradients in these, and most of them rotate counterclockwise. However, Coriolis is not that big a factor, and there have been some clockwise tornadoes in the United States. I wanted to use this one. This is per 10,000 square miles, how many tornadoes you get on average each year. So if you think about it, you're keeping everybody the same instead of the number of areas per state. And some of the states are much bigger than others, but Kansas actually gets the most per area. West Virginia does, only average one. But notice over here in Maryland, they average 10. So significant differences around the United States. Midwest, southern states get a lot more typically than the East and Northeast, very little up in the Northeast actually. And out in the deserts, not much either. This is just a slide with some safety rules for tornadoes. And tornadoes are really a major threat to life and property, as you can see. This is Joplin tornado. Uh, the interesting thing about the Joplin tornado was it was an EF5, went through downtown Joplin. The warning was issued right literally before it ever touched the ground. It was an outstanding warning by the Weather Service. By the time it reached the eastern side of Joplin, that was an hour later. That warning was for an hour and a half. So the people in Joplin, especially those in the eastern part, felt the tornado must be over by now because the warning had been out so long. So they came back out, and that's when they got hit with the tornado and people died. So the question became, how long should a warning be? It's still being studied to see what's the best timing for tornadoes. And here is the new scale put out 20 years ago now. Ted Fujita put the original scale out. He went and surveyed tornadoes, estimated damage from them. The enhanced Fujita scale, all that is they went out and got civil engineers who looked at the damage, and from the amount of damage, and I mean, they looked at trees, they looked at various buildings, how the building was built, how the car was damaged. There are thousands of photos out there that they took that literally are handed to the meteorologists when they do a survey, and they do the survey based on the damage pictures. Now, if a tornado is an EF4 and EF5, professional civil engineers will come out and look at the damage as well to try to determine exactly whether it's an EF4 or EF5. The Weather Service will make initial estimates, and here you can see the supercell. Typically, the tornado is on the southwestern corner of it, and here would be the heavy rain to the north and large hail just to the north of the supercell. Here you have that wall cloud where the winds come in from this into the cloud. They're already rain cooled, so you get the air coming in, condensing at a much lower altitude. Also, notice the top of the cloud goes well above the anvil, and many times it goes into the stratosphere on these type of storms. Wall cloud is again something, if you're out and you see this, where the flat base rotation on the bottom of the cloud, that is where you might expect to find a tornado. So I think that's about enough out of this. Let me know if you have any questions on all of this.